All right, in this lecture we're going to be talking about shell coding. We first mentioned this in the lectures on stack and heap overflows, as this is the code that we inject once we actually exploit a vulnerability. In this lecture we're going to be talking about how do you actually create this code and what are some of the properties and whatnot that it should have. So what is shellcode? Shellcode is just a set of instructions that are injected and executed by exploited software. So this is the code that runs once you've figured out how to do that heap overflow or the stack-based buffer overflow. You also hear this called as the payload of the exploit. The name shellcode just came from the fact that historically shellcode would typically spawn a command shell, and so that's where the name came from. Now, as we learned in the previous few lectures, one of the challenges during exploitation is figuring out where your code is. And so typically, shellcode is accompanied along with something that's referred to as a NOP sled. And this is the NOP sled is just a set of instructions that actually don't have any real impact on the code execution. The no op is the opcode is hex 90, and this is basically a single byte instruction that does nothing. And so this would be placed before your shellcode, so that if you transfer somewhere into the buffer of code, if you land in the NOP sled, then it will eventually transfer execution to your shellcode, which performs whatever function you're trying to do. The downside to the traditional NOP sled is that a huge buffer of a lot of hex 90 bytes is pretty easy to detect. And so what shellcoders and exploit developers have done is they create up a series of tools to help generate seemingly random patterns of bytes that have the same effect as a series of no-ops. So one type is called a multibyte NOP sled. And so as this shows here, these are all the different ways that the bytes at the top would disassemble to x86 code. So you look at the very bottom, you see the move EBX, and then you have a 32-bit value. That's if execution were to land at the very beginning of this buffer, where the BB is, then that's what it would disassemble to, those first 5 bytes. If it would land on the B0, then you'd have move AL BF followed by the rest. And so basically you can land anywhere in this buffer and you're going to be landing on valid code. So one of the things that you'll typically want to do with shellcode is leverage system calls. System calls in Linux, provide a powerful set of functionality that is pretty easy to invoke and call from your shellcode. All that's involved in actually invoking a system call is that you have the system call number, and so you can, if you search around online, you can find reference, or if you look at the kernel source, there's well over 100 different syscalls, but each of these have its own unique number, and so this number is loaded into EAX, and then you have the arguments for that system call are passed in registers. At least the first 6 are. Beyond that, they're passed in data structure. And so you load the arguments, and then you call the int 80 interrupt hex 80, and that's the CD80 is the actual opcodes for that. That's going to trigger the CPU. It's going to switch to kernel mode, and your system call will execute. So just as a little example of this, we're going to create a C file that right now is just going to call the exit function. So we'll compile this statically, and that way the actual exit function will be included in the executable, and so this would be the GCC command to do so. And so if we compile it and then we load it into GDB and disassemble the exit function, we see this code here. There's just a few instructions. And if you look at that code, you'll see that it's moving FC into EAX. And so if you look, and then does the call. Well, if you disassemble what the call is, that's essentially just invoking the interrupt, the int 80. But then there's another int 80 down below, and this time it's moving a 1 into EAX, and then you see the halt instruction. So this is actually two different syscalls that are being executed, this exit group and exit, both of which take one argument and is passed in the ESP plus 4, as you can see in the code below. But we don't need the exit group for our shellcode, and so what we're going to do is we're going to write some code in NASM, which is stands for the Net Wide Assembler. And as you see here, we just have a start routine. We're going to move 0 as a parameter into EBX. So if you recall from a few slides back where we showed the 6 registers that are passed, EBX is going to be the first one. And then we're going to use the syscall 1, move that into EAX, and then we're going to call the int 80. So here we run NASM to compile our shellcode, link and load it, and then we'll invoke it. So of course all it's doing is calling exit. So if we run obj dump, so object dump, to take a look at what's in our code there, you can see the instructions that we used in NASM. So very simple here. The one thing to note here is that with the exit code, I mean, obviously in most shell code, you're not really going to, the only time this really would become relevant in shell code is if you want your exploit your payload to exit cleanly. I mean, in general, just calling exit doesn't do anything particularly exciting, but this is just a kind of an illustration. So when you're testing the shellcode, there's a standard C template that a lot of people will use to actually test it. And so here we have a character array, which the character array just is encoding our shellcode. So if we look at those bytes there, the BB, 00, etc., and then we look at the bottom, in the middle of the diagram at the bottom of the screen, you can see those same bytes. So this is just encoding the instructions that we use there. And so that's one of the useful things about the object dump utility, is if you just want to quickly dump and get the bytes, it's one way of doing it. And so so then if we look at what's in the main routine, we define a integer pointer called ret. And what we're essentially doing here is just getting a pointer to the return address on the stack. And so it's getting the address of ret plus 2, right? Which is going to, just think in your mind about where that's going to be on the stack. And then we're overriding that pointer with a pointer to our shellcode above. So this is just a simple way of testing and running shellcode. And if you see at the bottom of the screen where we compiled this, ran the test, and of course it just exited as we would expect it to do. Now one of the problems you run into is that oftentimes the overflow or the exploit you're doing is using C arrays, so that limits our shellcode. It puts some constraints on it that we can't actually have any null bytes. And so typically with shellcode it needs to be either ASCII or Unicode text, upper or lowercase, no null bytes. And so there's a number of restrictions. And depending on the scenario, there might be other restrictions as well. And so if you look at our code below, there's quite a few null bytes, and so this is not going to work too well for us. The other thing is that these null bytes that are there are just taking up space. I mean, in general, you want your shellcode to be as compact as possible. There's no reason to have big, long shellcode if you can avoid it. So this gets to this notion of injectable shellcode. So this would be taking our code that we wrote before, which was very intuitive, easy to understand, and making it so that functionally it's equivalent, but there's 0 null bytes. So one of the things you'll see, first of all, is that literals are a major source of nulls. And part of that is because in the instruction where we're moving EAX1 or move EBX0, we're moving this into, what really is a very small number into a 32-bit integer. And so that's going to get, it's getting encoded. There's a lot of wasted bytes that we don't really care about. If we really only want those low 8 bits, you'll recall from one of our first lectures we gave just on Intel architecture that the 32-bit registers like EAX, you can reference their 16-bit value by the AX register, and then the AH and AL is the high and low 8 bits of the AX register. So to avoid the literal in this case, if we say move AL1, that's going to still assign the value 1 to EAX. It's just we're not going to be wasting, we're not having any of those null bytes. Another common trick is rather than assigning 0, using the move instruction to assign 0 to register, is to XOR the register with itself. So if you just think about the function of an XOR, anything XOR with itself is going to be equal to 0. And so you'll actually see a lot of compilers do this as well because it's just more efficient. It only takes up a single byte in most cases. And so that's what has essentially been done here. We've changed these on the left to the right, so now we just have XOR EBX EBX, move AL1, and then our interrupt. And so if we look at sort of a side-by-side or top and bottom comparison here, in the top you see our original code, which has all those unwanted null bytes, and then down below we see our injectable shellcode, which is not only more compact but also lacking any null byte. All right, so next we're going to be talking about actually popping a shell in Linux as an example. And so if you're doing a local exploit, then here's a simple C file that's basically going to pop us a shell. We're using what's called the execve function. And so you can, of course, look at the man page if you want to read all the details of that. But all this is essentially doing is this is passing the first argument is our command that we want to run, which is bin shell. So it's going to load a shell, and then passing the other arguments, parameters. So if we compile this and run this, then you can see that we've got a new shell that was created, and we can interact with that shell and then exit. So if we walk through, disassemble the code that we just ran, here we're moving, this is where we're moving, putting in the parameters, and this is the call to execve. This is just a pointer that's being moved. And here you can see the registers being populated with the values. And if we call that function, recall that's just essentially calling the int 80 instruction. And so the EAX or EBX, EDX, and ECX are containing, those are our arguments to our sys call that we're trying to make. So one of the things when we're popping a shell, or this applies in general when we're writing shell code, is that we want to write the code to be position independent code. So position independent code just means that we can use relative addressing. We're not hard coding fixed addresses, and this is really important because, especially on modern operating systems where you have things like ASLR and whatnot, where it randomizes the load address, but also just in general with exploits where we don't really know where exactly in memory we're going to be, we want to be able to use relative because we can be certain where we are relative to the rest of our code. And so if you look at this little sequence of code here, we're jumping down to the shellcode call, which is just essentially calling our shellcode, and we do a pop ESI. Now you may be wondering, well, what's that going to do that's interesting? Well, if you do a call, recall that that's actually putting the return address onto the stack. And so by calling our shellcode and then popping, we're essentially getting a pointer to, in this case, the argument bin shell argument once we pop ESI, because that's where the return address is going to be. And the reason why we use the short jump is because, again, that gives us a relative address. All right, so if we look at this in more detail, DB, again, is essentially just scratch space where we're putting our parameters. And we want to avoid nulls, so you can use the XOR technique when you're using relative addressing. That also makes it possible for you to do dynamic override or self-modifying code, because, again, you know where the code is, and you can potentially transform your code dynamically. But we can use position-dependent code in this case by referencing the ESI register, because once we've called our shellcode that and popped ESI, ESI contains a pointer, and then you'll notice in this code everything is referenced, all of the offsets are referenced from ESI. And so if we walk through this step by step here, pop red into ESI, so this gets the return address. XOR EAX with itself, that's just clearing EAX. This instruction here, we're setting the capital J to null byte, okay? Which, again, that makes sense because we needed to avoid nulls, and so if ESI plus 7, if you count on the bottom plus 7, that's going to take you to the J, and so we've XORed EAX with itself, so it's 0. So moving AL is just effectively moving 0 into that byte, so it's moving a null. This is setting up our first argument. So here we want to get the address of bin shell. So that's what the LEA instruction, the load effective address, is doing right there. And now we want to set the AAA to the address of arg1. So again, here we're getting a pointer to arg1. And then we also want to set the KKK to null. And so again, we're assigning, we have EAX is still 0, right? And so that's assigning that to null. This is the syscall number we want to for the exec VE is hex 0B. Here we're moving. This is again the address of bin shell, so the shell we want to execute. This sets up our arg2, the address of the string. In this case, arg3 is null, and at the very end, this calls our syscall. So this is going to pop our shell, and here we've got a series of our shellcode, which we've avoided null bytes again. We've used a few different tricks to do that and kept things relatively compact. So now we'll put our shellcode that we just wrote into our standard C template to test it. And if you run this, then you'll find that it will just simply pop a shell like we were going for. So relatively simple, straightforward example, but as you can imagine, this can get quite a bit involved depending on what functionality you're trying to do with your shellcode. So in Windows shellcode, it's a little bit different than in Linux shellcoding. In Windows, you're going to be looking at DLLs for most of the functions that you want to perform. There are system calls, but you're typically not going to use those in the same way that you do under Linux. A lot of the code typically is resolving the addresses dynamically, and so the effect that this has is this is going to make your Windows shellcode larger, because you're going to have more things to get proc address and other functions that are going to help you resolve addresses of functions you want to call dynamically. And one thing to note on Windows too is that the notion of popping a shell, like we were just going through under the Linux example, forget about doing that. You never want to do that in Windows, because if you just think about the typical Windows user, that's not the same. It's just not a typical thing that you would try to or want to do. All right, so now we're going to revisit. We talked a little bit earlier about position-independent code, and we saw the technique for having the call instruction to call to up to our shellcode, where then we pop that into a register. There's other techniques out there that you can use as well to try to get EIP. So EIP, if you recall, that's the current instruction pointer, and you can't directly reference EIP. There's no such thing as move something into EIP or move EIP into some other register. And so people have come up over time with a few different techniques and tricks for getting EIP. Calling, like we saw before, that's one. Here's a set of 3 instructions where what we do is first execute some dummy floating point instruction, so in this case FLDZ. Then we're going to call the FN, ST, and V instruction, which is going to get the instruction pointer, the last floating point instruction. Okay, and then we're just going to simply pop that value into whatever register, in this case popping in EAX. So after these 3 instructions, EAX is going to contain our current instruction pointer. Another technique that you'll see is to have a call for, which essentially is a more compact way of, if you disassemble it, it looks like on the left, but what actually ends up happening is that this is because when you call 4, it's going to go forward 4 bytes. So if you count 1, 2, 3, 4, that's the very last FF if we're just reading from left to right. And so the call is going to land on the FF. Well, it's going to disassemble to FFC3. So if you look, which over here, the C3 is the ret, but dynamically it's going to actually land on FFC3, which is the Inc EBX instruction, and then 58 is the pop EAX. And so again, this is going to get us the current instruction pointer. There's another variant of this where it's call +5 and then pop, and so it's just another way of doing it as well. Okay, so now we're going to shift gears and talk about different types of payloads that you'll deploy. So the first, and this is the simplest, is just your single. This is your completely self-contained payload. Does everything that you want to actually do. But what you find is that to keep things small and compact, but also to be a slightly more stealthy, people will do things in stages. And so a stager is a payload that is going to load and then execute a stage. And so the stage is a payload that's loaded via stager. And so this, to put this in practical terms, you can imagine you exploit a vulnerability, you run a little bit of code, and then the stage is going to do is it's then going to call out over a network connection and then download the larger payload, right? And so, or potentially kernel to user handoff. Anyhow, the advantage of doing this is that it's much smaller than a single payload. It's also less clear if this is detected by a security product or any sort of personal security product, then all they're seeing with the stager is that it sees, okay, this is just generically calling out over a network connection and downloading code. They don't actually see the payload of what is actually trying to be done. And so that's another, just from a stealthy standpoint, why these are typically used. So you can have local shellcode, you can have remote shellcode, you can have the download and execute staged shellcode, and then there's something we'll also talk about called egg hunter and omelet. So the local shellcode, this is typically used for privilege escalation. So that you're on your physical access to the machine, but you're an unprivileged user and you're wanting to be able to run things at a higher privilege level. And so that's where local shellcode really kind of comes into play. What you read about a lot more is remote shellcode. And so this is where the attacker is remote And the reverse we talk about here is, whatever the victim machine is, essentially connecting back to the attacker. And so while this is attractive, is that doing this bypasses things like firewalls and NAT, like network address translation, because you're now coming essentially from inside the network calling out. And so another type is where the attacker may bind and open a server port on the victim, so that this gives them a back door where they can just kind of directly call in and get access to the remote machine. And another type is where the shellcode is where there's some existing connection where you now want to reuse that as sort of your channel, as your command and control channel. And so many different things that you can do, but these are some of the most common types of remote shellcode. But the download and execute, this is most common for browser drive-by attacks. So you have there's some web address that's hosting malicious filers, running some malicious script, and so again your shellcode gets downloaded, saved to disk, and then executed. Staged shellcode is what we talked about earlier, where you have some stager payload that then is going to download a staged shellcode, and that's going to have your larger functionality. So again, the idea here is to have something smaller initially. Maybe it's doing a little survey, and then it's going to figure out what operating system, what the configuration of the machine is, and then it's going to pull back a larger piece of shellcode to do whatever the intended purpose is. Yes, egg hunter and omelet shellcode. This is, in some cases, you don't have, maybe there's limited space, and for any number of reasons, you don't necessarily know exactly where the bulk of your code is. And so this idea, in this case, the code you're trying to find is the egg, and so you have this small hunter shellcode that's injected at a predictable spot, and the hunter is searching for your larger egg, which is at some less known location. And so then the idea of an omelet is that where you have multiple small eggs and you want to try to combine those into one. And so that these come into play when you have different constraints on the exploit or where you're able to get shellcode into the system. So in the egg hunter omelet case, there's a number of techniques, and if you Google around for this, you'll see so there's some interesting papers that talk in more detail. But the idea here is with this NT access check and audit alarm is that it's going to, if we're scanning through memory looking for a particular pattern, first we want to make sure that we don't cause some access violation. And so the address we want to check, we can push on the stack, call this access check function, which will report back whether that would give us an access violation. And if it would, then that's not an address that we want to try to read from, because otherwise it's going to crash. And so you want a search technique that's going to let you churn through your memory space where your egg might be, but making sure that it doesn't actually cause a crash or access violation. So Metasploit makes this pretty easy for us by, you'll have an egg tag, a marker, and then a checksum stub. And so the idea is that the tag and the marker, that you can quickly and uniquely identify the egg, and then in case there's some false positive, the checksum stub will compute a checksum of the payload, and then that way you can be sure that you've found the correct egg in memory. And so here's, again, shows some of the lower level assembly code for that, where on the left here we're checking to see, is this readable? So you can see the calls to the check, access check and audit alarm. And on the right is where you can see the code for where it's scanning through and looking for the tag, and then the marker, and then where it could optionally insert the checksum. And at the very end, if everything checks out, then it's going to jump to the payload, and that's where the jump EDI is for. The other useful thing with shellcode is that you'll typically want to use some sort of encoder, and so this will create equivalent shellcode but have different byte sequences that have special properties that are attractive. For one, if you want to evade filters, you can set restrictions on the character set. So generate shellcode that will not use any characters that's going to cause problems. If you want to avoid some of the antivirus and IDS systems, have it. A lot of these may have things like static string detection or look for specific instruction patterns. You can have the encoder generate code that's going to avoid those, as well as size. So if you want to try to make sure it's at a smaller size. Some of the more complicated encoders will also have a decoder routine that is left, which is people refer to as a decoder stub. So the idea is that it gets the shellcode gets encoded. It's encoded to meet all these constraints that you place on it, and then at runtime, this decoder stub is going to decode that and execute the code. So some of the techniques that are used to evade things like IDS systems, you'll hear the terms polymorphism and metamorphism. And the idea here is that the code is changing each time it runs. So in metamorphic code, metamorphic is more sophisticated and difficult to detect than polymorphic. In metamorphic, you're changing every time. So this is changing to equivalent code. So there's different, as we've seen in some of the examples before, there's many ways of doing a particular computation in assembly, moving 0 into register, XORing it. These are all examples of equivalent instructions that do the same thing. There's also, you can have multiple instructions that do an equivalent thing as a single instruction. Adding something and then subtracting it is essentially a no-op, right? Well, let's say you add 5 and then you subtract 4, that's the same thing as adding 1. So these are all things that can be used to avoid pattern detection. Polymorphism, you'll have, it might have different decoders. A decoder may, when it generates a new copy, use a different encryption key so that you have, different signatures. But the idea is at runtime, it decodes or unravels itself as it executes. But with those, there is, at least with polymorphic, something that is fixed, and that ends up becoming something that you can detect potentially. There's a whole slew of different kinds of encoders, and as you play around with Metasploit, you'll see you can kind of experiment and see what the output of these different encoders look like. The Shellcode encoder is an XOR additive feedback encoder. The name itself just translates to nothing can be done about it, and the detection is very computationally expensive, and especially for network devices. So if you have network devices just sitting and looking at traffic, detecting this is going to be very hard. And so this is just one of the many encoders that is available within Metasploit. There's also ASCII art encoders. So the idea here is that you have some sort of artwork that's using all ASCII characters, but if you actually look at the bytes for that, that can translate to encoded code for your shellcode. And so within Metasploit, there's a generator called the MSF payload. And so this is a shellcode generator. We use web, console, or command line. If we look at the help for this, here's just a few examples of common types of shellcode. Connecting back and spawning the command shell, listening for connection, spawning command shell. So there's all sorts of different options here that comes with the framework that you can use. There's the MSF Encode program, and so this is, again, a machine code generator, and so you can specify here, what architecture you want to encode it as, characters to avoid. So we talked a little bit about that before. What encoder should be used, and so a lot of powerful options. If we look at to show all the encoders that are available, you can see here there's quite a few. Down below, further down, you can see the Shellcode Generator that we mentioned earlier. And each of these, of course, has a little description of what it does. So again, here's the different encoders. You can use the Shellcode Generator and the encoder together, as you might expect, if you want to generate your custom shellcode. And so if you look at the screen here, we have a few examples of how you might use those. In the bottom window, we're producing an executable called Trojan that we have a payload that's doing a reverse TCP connection, and we pass it the host and port. So a lot of different options that you can use this for. And then this can be used as, you can also use this to generate custom shellcode in C arrays, which is also useful. There's also an MSF Venom tool, and that's just simply the combination of the payload and encoder. So again, here's an example of using MSF Venom. We want to create a Trojan. And then on here, we're just showing an example of, we've created something, loaded it to an AV engine, and you can see that it scanned it and detected it. In this case, this is an older example from 2009, but it has is able to be identified as matching a few signatures. So here's another example of, if we want to make some shellcode, sort of a RickRoll. The idea here is to creating something that looks attractive to the user to sort of entice them to click on it. And so here again, we're using the MSF payload and MSF encode, and using the Shellcode Generator encoder. And so you can see down below, that's the resultant shellcode that we can nice, easy copy paste C array that we could use in a program. And for more information, you can go to the Metasploit site and shellstorm.org. Went through a lot of the examples at the end somewhat fast. The easiest way to familiarize yourself with this is to download Metasploit, or maybe set up a Kali Linux VM that has all the Metasploit and pen testing tools already set up, and just play around, run through some examples, try generating and encoding some shellcode, and you can also try using the C program that we had before as just a simple way of testing shellcode, where you generate an array, plop it into that C file, and then run it and just see what ends up happening. So another great book is I think we've mentioned it before in other lectures, is the Shellcoders Handbook. And that one, again, also goes into a lot more detail, not only about shellcoding, but also it talks about stack overflows, heap overflows, and all sorts of other exploitation topics. All right, and that concludes this lecture. So as always, if you have any questions, feel free to email us, and we will catch you next time. Thank you.